with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have to meet and study your creation. Just pray that you be glorified today in what we do, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I need to talk to you guys more about the so-called Cauchy Euler problem. Sometimes it's also called the equidimensional problem. And it comes up in a variety of applied problems in science and engineering. Like, for example, if you try to solve the problem of waves on a drum and you find yourself using polar coordinates, it turns out that the Laplacian ends up giving you like a Cauchy Euler equation for the radial coordinate, if I remember right. But anyway, the Cauchy Euler problem, or the equidimensional problem, is as follows. And we're just going to look at the n equals 2 case, I think. Although, admittedly, here is a place where I could go to n equals 3 and it wouldn't be crazy. So, I mean, I wouldn't put it past me, but focus most of our attention on n equals 2. And so an arbitrary Cauchy Euler problem, order 2, looks like this. ax squared y prime prime plus bx y prime plus c y equals to 0. Now, the first time I saw this was on the, if I remember right, the final exam for my differential equations course. He put it there for the first time in my course. I was like, wait, what? And but he gave us a hint, and the hint was try y equals x to the r as a solution. And that's pretty good advice, you know, because if you do that, it will quickly lead you to where you need to go. So if we do ax squared x to the power r, 2 derivatives, plus bx x to the power r, 1 derivative, plus c x to the power r equals 0, plug it in, right? What happens when we take 2 derivatives here, we get x squared r times r minus 1 x to the r minus 2 plus bx r times x to the r minus 1 plus cx to the r equals to 0. But if you look at this, this is why it's called the equidimensional problem. It's because, you know, so if x has units of length, what's the units of d dx? What do you think? If x has units of length, what does d over dx have the units of? No. 1 over length, right? 1 over length, d dx. So you have 1 over length squared times length squared. You have length times 1 over length, right? And then you just have whatever the units of y are left here. So the point is that, you know, that's why it's called the equidimensional problem, among other things. But anyway, if you look at this, notice how the x to the squared and x, see this? Everything's x to the r here. So I've got a times r minus 1 plus br plus c, all times x to the r, is equal to 0. So this tells us that a r times r minus 1 plus br plus c equals to 0. This equation right here, I would say that it serves as the characteristic equation for the Cauchy Euler problem. All right, and I showed you last time at the end of class that, you know, we could write down solutions from this. So let's look at some more examples. So example 1. Let me see if I can think of something here. Yeah, let's put b and c both equal to 0. That makes it easy for me. Then we're looking at, and we'll just let a equals to 1. That's the case I'll look at here. So I'm looking at x squared y prime prime equal to 0, right? It's kind of silly because You know, so my equation becomes r times r minus 1 equals to 0, which tells me r1 equals to 0, r1 equals to 1, right? So, so y is equal to c1x to the 0 plus c2x to the 1, right? In other words, y is equal to c1 plus c2x. Now this is hardly surprising, is it? I hope this isn't surprising. How could you have also solved this equation? This should be very unsurprising, right? What could you do there? How about just divide by x squared, right? And integrate twice. I hope we would all get there, yeah? So this, of course, has second derivative 0. Let's look at another example that's perhaps a bit uglier. What if we had, oh, I don't know, let's just try y x squared y prime prime plus xy prime equal to 0. We'll try that out. So this gives me r times r minus 1 plus r equal to 0. All right. Which gives me what equation here? R squared minus r plus r equals to 0. Ooh. Uh-oh. What do we got? We've got r squared equals to 0. Right? This is a second order differential equation. How many solutions do I need? Like the general theory says that I'm looking for y equals to c1y1 plus c2y2, right? Where y1, y2 is linearly independent. You know? We're looking for linearly independent fundamental solutions. With r squared equals to 0, this gives me r equals to 0. I only get one solution. What should I do? Right? Because I've got y is equal to c1 x to the 0, which is, you know, which is just 1, right? So what gives? I need to do plus c2 times something. What should I do? Any ideas? So there is a technique back in one of the earlier chapters to derive a second linearly independent solution. That might work here, but there's something much cooler to notice, and this is a technique that generalizes to many other problems. And that's to notice that if we have a solution that depends on a parameter, sometimes we can use that to our advantage. So notice that when we had lambda repeated, right? We start out with, let's say, e to the lambda x, right? That was our fundamental solution, right? And you guys remember what we did. It was x times e to the lambda x was the second solution. That won't work here, all right? If I was to try that, you could try putting x here, right? X times 1. And if you try x, it won't work, right? The derivative of x is 1, so that gives me, this term gives me x. If I try x prime prime, I get 0, so I would get 0 plus x equals to, well, it doesn't equal to 0, right? So x is not a solution here. Multiplication by x won't work. But check this out. If I take the partial derivative, not with respect to x, but with respect to lambda here, all right, then that gives me e to the lambda x times the partial derivative with respect to lambda of lambda x. What's that? This is just giving me x e to the lambda x, you see? So if we take the partial derivative of a solution that we already have with respect to the parameter of the solution, it will produce the next solution in the repeated root case. By the way, this continues working. If I take second derivatives with respect to x, I bring out, with respect to lambda, I bring out the x squared, and so forth, you know? So if we follow this idea for the Cauchy Euler problem, right, I'll put it up here. We want to take partial r of x to the power r, right? How do you do? So what's that look like? What's the partial derivative with respect to r of x to the r? Notice that the variable here is in the exponent. This is an exponential with base x. So we do log of x times x to the r. Right? In fact, that's what y2 is here. We put log of x. I'll put x to the 0 here to emphasize the pattern, x to the 0. So the answer in the repeated root Cauchy Euler case is we take and we multiply by log x in this context. So we got c1 plus c2 natural log of x. That's the solution. The general solution to that problem right there. All right, so so example 2, let's see if I can, example 3 here, come up with another one. What if we have I'm a thinking. So x squared y prime prime plus 3 x y prime plus y equals to 0. All right. So we get the following characteristic equation. We get r times r minus 1 plus 3r plus 1 equals to 0, which gives me r squared plus 2r plus 1 equals to 0, which gives me r plus 1 quantity squared equal to 0. Look at this. So we have r equals to minus 1 repeated, right? So therefore, following my last example, we get y equals c1 x to the minus 1 plus c2 x to the minus 1 times the natural log of x. I guess I should mention, I'm assuming a certain context here, which is that x is positive. Same for my last example. Right? If x was less than 0, then the solution is the following. Or if you like, you can put a minus x there, because if x is less than 0, the absolute value of x is minus x. This would be the solution. Now, of course, you could rewrite this, both of these you could rewrite like this, right? c1 over x plus c2 natural log of the absolute value of x over x. Like, maybe that's the right way, probably that's the right way to write the general solution if I don't tell you x is positive or negative. Most often I just say x is positive because I don't really have interest in taking points off students for this, because like pretty much all of the Cauchy Euler problems you'll ever find in the wild, they almost always have the context of like positive independent variables anyway, so it's not something that really needs to be corrected so much. The other issue I try to correct in here is like, putting a minus with a square root when you need it. That does require correction, because those do actually occur in the wild, so to speak. Example 4. Let's see if we can come up with another one here. How about, excuse me, x squared y prime prime plus, 5xy prime plus y, plus 5y. Yeah, plus 5y equal to 0. Let's see what happens there. All right, so we've got r times r minus 1 plus 5r plus 5 equal to 0. This gives me r squared plus 4r plus 5 equals to 0. Oh, this is one of my favorite quadratics. We complete the square on this, what happens? We get this, right? So this tells me that r, in this case, is minus 2 plus or minus I. All right? So how do we deal with that? What is the solution in this case? Right? What do we mean? I mean, I really should probably define for you what on earth we mean by x to a complex value, right? How should we understand x to alpha plus I beta. Like, what's the definition of that? All right? So the definition of this is simply as follows. It is x to the alpha times x to the I beta, which I can understand. I mean, I'm still kind of deriving it at the moment. We'll get to the point of what you should just remember in just a second here. But take exponential of the natural log of x to the I beta for this course. People in my complex class, ignore this. It's wrong. But it's a useful lie for our current context. Exponential. I mean, it should really be the complex log, right? But anyway, come take complex with me, and I'll explain that more to you. Complex now has no proofs. Ask Jordan, he'll tell you. There's no proofs in there. It's safe, right? Say it more believably. More believably. There's no proofs. It's just computation. It's easier than this course. Spread the word. Let's see here. No, complex is a challenging but rewarding course that if you're an electrical engineer, you'd be wise to take. But anyway, actually, if you're any kind of engineer, you'd be wise to take. But so what this means, of course, then we just drop back to our Cauchy, our Euler identity, right, which says an imaginary exponential can be written in terms of sines and cosines. So you could take the thing I'm about to write as actually the definition for our purposes in here, which is that it's x to the alpha times cosine of beta log x plus I times the sine of beta log x. All right, so this, for all intents and purposes in this course, serves as our definition for x to the alpha plus I beta. And for the sake of common human decency, we're going to assume that the context here is x greater than 0. All right? If x is less than 0, then you got to replace x with absolute value of x. Big deal. All right? So with that context, we can now write down a complex solution to this Cauchy Euler problem. What is my complex solution? Well, it is x to the minus 2 plus I, like that. All right, so that's my y1. Actually, let's call it z1 because it's a complex solution. Complex solutions are twofers, 2 for 1. So because you get two solutions, two real solutions for the price of one complex solution, x to the minus 2. And then we got ourselves here cosine beta is equal to 1. Right? Alpha equals to minus 2, beta equals to 1 here. So I got cosine of log x plus I times the sine of the log of x. Right? And so from this, I can say y is equal to c1 times the real part of z1 plus c2 times the imaginary part of z1, which in this context is c1 cosine of the natural log of x divided by x squared plus c2 sine of the natural log of x over x squared. There should be no I in the real solution, right? The real solution, it's a team effort of y1 and y2. You know there's no I in team, right? There we go. Sorry, I regret that. No, I regret nothing. So there you go. This is what happens if you have a complex solution in the Cauchy Euler problem. Now I've shown you all the cases. Real distinct, repeated real, complex. This is all that can happen for a quadratic, right? So now you know it all. I hope you see that the Cauchy Euler problem is not a bad problem for the next test, right? I mean, if I was up against a complete power, if I had a choice between a Cauchy Euler problem and the complete power series solution at an ordinary point, I would choose the Cauchy Euler problem. It is way, way easier, right? But the Cauchy Euler problem is merely the backdrop, the setup, the so-called indicial equation for what's known as the Frobenius problem. Let's look at the Frobenius problem. This I'm not going to try to write out. All right. Where'd my cord go? Oh, here it is. So I'm trying to hide it back here. So what we're about to do is to talk about the so-called Frobenius problem. And so at the start of the Frobenius problem, there is a need to define something called the a regular singular point. So in short, well, I'll show you the definition. I don't want to belabor it today. If I can find my notes. Got too many things open. Here we go. Partial differential equations. Well, this is a little bit past where we are. Whee! All right. So here, I'll just go through this stuff somewhat quickly. We talked about ordinary point before. That means that P and Q are analytic at x naught. It's a singular point if it's not an ordinary point. It's called a regular singular point if when you multiply by x minus x naught the P, and if you multiply by x minus x naught squared the Q, those are analytic at x naught. What that means essentially is that yes, P and Q are divergent at x naught. Technically speaking, they're undefined, but by simply multiplying by x minus x naught or by multiplying by x minus x naught squared respectively, we clean them up. We basically remove the singularity, and you're left with a function which is defined at x naught, indeed analytic at x naught, which means it has a power series expansion. So that's the context, and that is indeed the context of the Cauchy Euler problem, right? Because if you look at, if you look at the Cauchy Euler problem, if you divided it by x squared, you'd have your P is 1 over x, and you'd have your Q is 1 over x squared, and x times 1 over x is 1, and x squared times 1 over x squared is 1, and of course 1 is analytic. So here's some silly examples. The constant coefficient problem is ordinary everywhere. There's no singular point. This one right here, if you divide by x squared plus 1, you get this, which gives us a singular point at plus or minus I. It happens to be a regular singular point, because if I was to multiply by x plus I or x minus I, I would be left with something which is analytic. Again, I'm not going to stress like this. So I don't test on this, because to understand what I just said is complex analysis. All right, so I don't have a piece about testing this aspect of it in here, but in terms of language, we do need a little bit of this language. So there are also points, there are irregular singular points, which means that it's not a regular singular point. Anyway, let me get to the point. Let's move past this. So this is the Frobenius method. So suppose we want to solve y prime prime plus py plus qy equals to 0, right? Then how do we do this? So first of all, we're going to focus our attention on the singular point x naught being 0, because if you had a singular point at A, you can transform the problem to this, and that makes the singular point which was at A become at 0 for the new problem. So there's no loss of generality in just treating the problem with the singular point at 0. So let's just focus on that. These problems are bad enough with the singularity being at 0. So let's focus on that case. So the thing is, if we have a regular singular point, that actually means that P of x and Q of x have what are called Laurent expansions. These are Laurent series. A Laurent series is like a power series, except you add a couple of reciprocal terms, right? So the thing is, if I multiply this by x, it becomes analytic because it's just a power series when you cancel out that x. And if I multiply this by x squared, it becomes analytic because you cancel out the x squared, right? So these are analytic, all right? It turns out that the domain for a Laurent series is like an annulus. So it's, or a punctured disk maybe. So like you're missing the singular point in the middle, but then it's like on a punctured disk around that. So the way that works is essentially it's going to be like a punctured disk, and that disk will be as big as it can be until the edge of the disk bumps up on another singularity in the problem. So if you think about what that means in terms of the real axis, as these like solutions intersect the real axis, it means your solution is going to be defined from the regular singular point out to some furthest extent that defines the punctured disk, which bumps into another singularity. If there is no other singularity, if there's just the regular singularity, your domain's going to be from the singular point, not included, out to infinity, or from your singular point out to minus infinity. That's what happens. And that pretty much we don't work problems with more than one regular singular point, so like relax. It's always either to infinity or minus infinity, the solution. The domain, let's not worry so much about domain. Let's just talk about how we solve it though. This is the method of Frobenius. And at first glance, when I saw this, I was like, what? But that's not different. That's what we already do. Isn't this just a power series? Well, not exactly. Because notice that the solution we're going to plug into here, it's got coefficients. It's an infinite series, right? But this doesn't have to be a power series, you see, because that r doesn't have to be an integer. It could be a half. Then you've got an infinite series of like the square root of x plus x to the 3 halves plus x to the 5 halves plus x to the 7 halves. This you did not do in calculus 2, right? Even the most ridiculous of calculus 2s will probably not cover this, all right? I mean, I don't cover it. I'm pretty ridiculous. So this is new, all right? But it turns out that the analysis, the calculus of these kinds of series is pretty forgiving. You still can do term-by-term calculus. You can still do term-by-term integration. Like the integral of the series is the series of the integrals. The derivative of the series is the series of the derivatives. So like when I differentiate, I just get a sub n times n plus r times x to the n plus r minus 1. Because they're still power functions and they differentiate like power functions, and the second derivative's over here, right? So how do you solve these? Well, you plug it in. All right, you just plug the Frobenius solution into the differential equation and you get this to deal with, right? And then of course you can make a substitution to make all the power functions match up and combine things. Well, anyway, first I have to multiply these through, right? So as you can see, there's a lot to process here, right? Like for example, if I want to look at the lowest order, what would it be? If I want to find constant terms in here, what would I look for? Are those even here? Like n equals 0 is the lowest order here. What's that give me over here? R minus 2, right? What happens? This x squared multiplies the x to the r minus 2. What do I got from this then? X to the r. How about this one? The lowest order here would be from this p0 times x times n equals 0 term, which gives me a p0 times an x times a a0 times r x to the minus 1. So x to the minus 1 times x gives me, well, there's also an x to r here, right? So if you simplify this, the lowest order term, again, is multiplied by x to the r. Down here, q0, lowest order term, n equals 0, x to the r. You should recognize this. This is exactly what I started class with. This is the Cauchy Euler thing. N equals 0 is the Cauchy Euler problem, right? At the lowest order, you run into the Cauchy Euler problem. This defines what is known as the indicial equation. So as we process this, the lowest order in the chain of all those equations for all those infinite coefficients is the indicial equation. So the indicial equation, notice that a0 is everywhere. So you get no condition on a0, right? But you do get a condition on the index r, right? And this is why this is called the indicial equation. It's the equation for the index. It just so happens with the Cauchy Euler problem that the indicial equation is the characteristic equation, and you don't actually need the full series. So we'll see that here. But Now, like n equals to 1, at n equals to 1, you've got this to deal with. All right, you got to solve this thing. N equals to 2, x to the r plus 2, you get these things to deal with, right? So let's look at one with numbers in it and see how it goes. Of course, let's see here. So 3x y prime prime plus y prime minus y equal to 0. X is a regular singular point. Great. That means I can apply the method of Frobenius. My Frobenius solution is this, which, whoa. I guess I can rewrite like that. Interesting. Why did I do that? Anyway, it's been a minute since I wrote these notes, but y prime then differentiates to give me this, right? Wait, what? Oh, n equals 0. I don't know why I wrote that. I guess we'll get to it in a second. But so why differentiating this gives me that. I was trying to differentiate this, and I couldn't get it. But of course, notice n equals 0 is here. So I'm differentiating this one to get to that one, which is fine. And when I differentiate twice, I get, the n plus r times the n plus r minus 1, x to the n plus r. I would have a minus 2, but notice I've got a multiplication by x, right? So the minus 2 becomes a minus 1. And of course, I got the 3 from out here. So I get this. So I think what I'm doing, guys, the reason I wrote this here is because I'm trying to add together 3x y prime prime and y prime and y. And I'm anticipating that I'm combining all three of these. So to make that happen efficiently, I'm just changing the sums so that they're all... I'm doing what you wanted me to do the other day, Jordan, which is to meet in the middle. See, I've changed my powers to all be of the same format. And I didn't choose x to the power j, right, or j plus r. I did x to the n plus r minus 1 on all three of these. That just, for whatever reason, seemed convenient to me in terms of the calculation here. See, because then I can combine all three of them into one foul overarching equation that should be equals to 0, my bad. And so at the lowest order, we get the initial equation, which is 3r times r minus 1 plus r equal to 0. And then from this, we can extract a recurrence relation that we got to solve. Namely that a sub n is equal to a sub n minus 1 divided by n plus r times 3n plus 3r minus 2. All right. Well, the initial equation gives us two solutions, namely 2/3 and 0, right? And so these two different initial equations are going to lead to different outcomes for the recurrence relation. Now there's two different kind of paths you could go down here. The one would be to try to solve the the recurrence relation for arbitrary r. I don't really recommend that, I don't think. So what I'm going to do at this point is I'm going to put in the r equals 2/3 and just process what it looks like. Here's a1, a2, a3. These are the patterns that we get from plugging in the index 2/3 into this and working out the recurrence. So we end up with this lovely formula here. And so the 2/3 index solution works out to this. You can factor out an a naught. You have x to the 2/3 plus this beautiful function right here, which is not anything that is like elementary. This is a special function of some sort or another. Notice the 2/3 power here. That's nothing like exponentials or sines or cosines. It's something much more insidious. On the other hand, the r equals 0 case, again, we plug in the 0 and then we work out the recurrence relation, and after a bit of processing, we can find our way to this being the pattern. All right? And so that's my second linearly independent solution to the second order problem, and here you go. This is the general solution. All right? So, some things I can just kind of come in here and, just start calculating and see how it goes, just kind of like freestyle and just riff, hope it works out. This is not that. This problem ate a week of my life. When I first came to this stuff, it took me a while to really grasp what was going on here. These are non-trivial problems. These you should not work by yourself. These you should work with somebody else and check your work as you go, all right? For sure. And obviously, the full Frobenius problem is not a reasonable test question, right? it's borderline reasonable on Tuesday, Thursday. It's definitely not reasonable Monday, Wednesday, Friday. So if it does appear, it appears as a take-home problem. But it is important to know about. It is part of the course. Let's see here. So, and also this method of Frobenius, it defines a lot of the important special functions which we need for solving interesting partial differential equations of mathematical physics. Things like the Bessel functions, the Airy functions, things like this. They're all defined in terms of series which are Frobenius-based series. Here's another one. X squared y prime prime plus 3xy prime plus y equal to 0. So we put it into its proper format, figure out the initial equation. We actually have -1 repeated in this case. And so if we plug that in, we get this. Collecting like powers, I work my way to here. And so we see that we have, well, what happens here? N squared minus 3n plus 2. What is that? What happens with this equation? Is this non-zero? Well, I say if you put n equals to 0, you get 0 times a 0. So you don't get any condition on a 0, right? And on the other hand, if you put n equals to 1 or greater, this works out to 0. I mean, this works out to something non-zero, rather. So like, let's see here. This is n squared. Notice that there's a minus n minus 2n, so the 3n cancels with this when you multiply it out. So we get like n squared plus 3, I think. That's not, I'm sorry, the screen's shaking, it's bothering me. we got plus 2 here, and minus 3 here. So n squared plus 1. Is that right? So if I put n equals to 0, how do I get 0 for n equals 0? I don't see that.
No, you'll get a plus 2 minus 3 plus 1.
Oh, right. So I'm doing something wrong with my algebra. Oh, does this just work out to n squared? Because I get plus 2 minus 3 plus 1. So this just simplifies to n squared a to the n, right? A sub n. So no condition on a sub 0. But every higher n, we've got something non-zero times a sub n equal to 0, right? Which means that a sub n is 0 for n larger than or equal to 1. I mean, this is the Cauchy Euler problem. This is how the Cauchy Euler problem works out from the Frobenius method. All of the higher terms, except for like the a sub 0, in this case just the a sub 0, are 0. And of course here we just get one linearly independent solution from the direct Frobenius method. And then, like I was telling you guys, since it's a repeated root, we pick up this other piece. In fact, we worked this problem. Oh no, we didn't work this one. We worked something similar earlier. Let me go on here. The next one, x squared y prime prime plus xy prime plus 4 minus xy equal to 0. So here, again, 0 is a regular singular point, and if I work through the Frobenius method and plug it in, I work my way to this character right here. My initial equation is this equal to 0, which simplifies to r squared plus 4 equal to 0, and here's my recurrence relation, all right? Oh, so again, the initial equation can work out to be complex, in which case we're getting a complex Frobenius solution, which means that the coefficients should be understood in the complex sense. And so here's how that works out. I just work out the first couple of them. And my complex Frobenius solution would have the form a sub 0, x to the 2i times this business. So here a of x is the real part of all this, and b of x is the imaginary part of the part in big parentheses. On the flip side, x to the 2i, it is what? This is actually cosine of the log of 2x plus sine I times sine of the log of 2x, So when I multiply that complex thing times this complex thing, I get cosine times the a, cosine 2 log x times the a from this times that, and then I get a minus because the plus I sine log 2x times that I gives me a minus, so I get minus sine 2 log x times this b of x. And so that's my, when I multiply out the complex solution, I can write it like this, and then this is the real part, and that's the imaginary part, and so my general real solution has this form. All right, I've only found the first couple terms in a of x and b of x in this problem. Like, they're up here. All right, so yeah. So that happened, and I would just, if you read my notes here, I keep mentioning a book by Rabenstein, and that is a masterful. Like, if you want to see a book that really goes beyond Nagel, Saff, and Snyder, but it's still at more or less your level, Rabenstein's the thing to look at. It's quite beautiful. His calculational techniques are better than mine, for sure. And anyway, so this one here, the next problem, we end up with 0 and minus 2 for exponents. Something funny happens with the Frobenius method. When the indices differ by an integer, you get yet another case. Because you can have it that when the indices differ by an integer, that the y1 and the y2 that you'd like end up being the same solution as it happens. And so when I work through all of this just to get to the point, because now it doesn't have to happen, I think, if I remember right. Like, it can be the case that when the indices differ by an integer, you have to do something different, but sometimes you get two solutions. This one here, though, after I work out the algebra, I find my way to this solution here, and this is from index 0. So we end up getting this is our Frobenius solution for index 0. Of course, we need to find the other solution, find y2. We're going to look at index minus 2. And when you plug it in and work it out, you have to remember this, the boxed equation there. We plug it in and work it out. Our second solution works out to this, which actually has the same form as the original solution. In fact, the second solution, the second solution has the same form as the original solution, except for the 0th term, as it turns out. So, like, basically, you don't need to conclude all this already, because you've already got it. If you take a linear combination, if you take a scalar multiple of the first solution, it's like all of that's already in here. So we can ignore all that for the second solution and just keep the 0th term. And so this is the solution in this particular case. This is linearly independent from all that. So that's a general solution. I'm just saying it's ugly. All right, it's ugly. This is all in your book, in this like really ugly theorem with like 5 cases, but here is a derivation of why the repeated root technique thing I did today works. Like, this is why, if you have a differential equation which depends on a parameter, in this case lambda, if you take the solution that works for lambda and you partial differentiate with respect to lambda like this, and you commute the order of differentiation and the linear operator, then you can prove that you get 0. Like, this is a sort of derivation of why that partial differentiation by the parameter works for both problems. It's not an accident, it's a general feature for such differential equations. So, like, generically speaking, in the repeated root case for the Frobenius problem, you have your first solution, which has the form x to the r1, sum n equals 0 to infinity of a n r to the 1 x to the n. You find the second solution from that theorem I just mentioned, which is basically to take the partial derivative of this with respect to r1. And when you do that, you get a log, but you also get another infinite series, which is formed by the derivative of your coefficients with respect to r1. So to make this good, you'd actually have to solve the initial equation. You'd have to solve the recurrence relation, keeping the r dependence manifest. You'd have to keep the r dependence manifest to actually do this calculation. But anyway, do I test on this? No, right? Is there a Frobenius problem in your homework? Yes, but is it this one? I sure hope not. Probably not. Hopefully the one in your homework will either be, in all likelihood, the one in your homework probably has like distinct real roots. So it's like one of the first examples I worked here, where pretty much the method is the same as the power series method. You just plug it in and work out the equations. So any questions? That's all I got in my notes on this stuff. But yes, no, maybe so. Let me show you guys something. Give me a second here. I'll show you something. We got a minute, right? If I can find it. I wrote a paper with my brother on some of this stuff, and if I can find it. Oh, rats. Well, yeah, here's a paper. Here's a talk I gave on it. That'll work. So, so what I did here with my brother, Bill, is we worked out the method of undetermined coefficients, but also for Cauchy Euler problems. And it turns out that you can do that. I'll get to the point here. So, let's see here. Like if you look at the Cauchy Euler problem, t squared y prime prime, blah, 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 with a non-homogeneous term over here, right? Then I figure out the annihilator for that is such, and so we get a solution set of this, and that gives us a particular solution of b1 times root t, and you plug it in, and that's the solution. So, uh-oh. Oh, no. Oopsies. I feel like I'm supposed to have 3 log t here. Look at that. You know, I gave this talk once. Nobody corrected me. That's sad. Oh, come on. Let's see if I can find another one. So basically, we showed that you can solve the Cauchy Euler problem and a host of other problems by essentially the same method that I showed you guys, by the annihilator method. That like totally generalizes for a wide class of differential equations, as long as you can write the differential equation as like the polynomial of an operator. But anyway, I will shut up. I don't have enough time to explain this today. I don't know why I started. I'm sorry. Go on your business.